Thanks, Amory. So the second cloud-based tool that I want to highlight today is RAM Concept's PT Design Optimization feature. This feature uses intelligent genetic search algorithms to compare thousands of possible PT design alternatives and then automatically eliminates those with design failures and helps you select the lowest cost design. The feature was first released in RAM Concept version 6.5, which dates about 5 years ago. And currently, all licensed RAM Concept users have access to this feature as part of their paid subscription. Let's start by looking at a very simple example consisting of 3 spans, 2 cantilevers, with variable low point profiles in each span and variable high point profiles at the cantilever. One option for finding the most optimal solution is to evaluate all of the different possibilities. So for this example, if we keep the tendon profile at the interior supports at their maximum elevation, respecting cover, and consider changes to the tendon quantity and tendon elevations at the other low point locations only. And then if you refer to the table there, use the value ranges that I've indicated with the increment values, we find that there are over 127 million permutations, even for this simple problem. You might be thinking to yourself that you could intuitively select the most optimal solution, since this is such a simple case. And yes, I concur that that might be possible. However, in more complicated and irregular floor slabs, which are typically constructed today, that assumption probably doesn't hold. You might also be thinking that you could intuitively eliminate some, if not many of the possible solutions based on either prior experience or other design methods like load balancing. Again, while that may also be true, neither of those methods or experience guarantees that the final solution that you arrive at is truly the most optimal design. So what are we to do? Well, one possibility is to utilize cloud computing to analyze all of the possible solutions and compare them to find the most optimal. While the use of a large number of computers in parallel certainly helps, trying to analyze all of those possible configurations again in a very complicated model could still take months or even years. So obviously, cloud computing alone can't solve the problem. We need a more intelligent way to narrow down which trials we calculate. And this is where genetic algorithms come in. Genetic algorithms are an intelligent way to select which trials to calculate and which to skip. They start by describing the problem into a chromosome, or which consists of real structural parameters such as number of strands or profile elevations. You can see examples of 2 such chromosomes or trial solutions at the bottom of the screen. Each of those complete set of chromosomes could be then evaluated or analyzed in concept to see how good or bad it is. The genetic algorithm starts off with an initial population of chromosomes, which are randomly generated. Then the algorithm uses crossover and mutation to create new chromosomes or possible solutions. And those 2 concepts are depicted graphically there in the lower right corner of the slide. Crossover is swapping different parts of different chromosomes. Mutation refers to randomly changing one of the parameters in a chromosome. So as part of this process, the best chromosomes from each population are kept and then bred to create new chromosomes to evaluate in a subsequent generation. For the evolution to work, we also need a measure to evaluate the solutions. And speaking in terms of genetics, we select them, we want to push the fittest chromosome forward. For PT slab design, we can use material and labor costs as a fitness measure. And for our purposes, this would consist of the cost of all the reinforcement. But another important aspect of a fitness value is how design code failures are processed. In the end, we want to eliminate any of those possible solutions that are subject to a design code failure. We want a valid design. And one way we could do that is by introducing a failure cost penalty that inflates the cost of the solution for any and all design code failures. This is a typical convergence chart for a PT optimization run in RAM concept, and I feel that it offers a good visual of how the optimizer converges to an optimal design. In the early iterations, it is working to find a valid solution. A valid solution is one with no design code failures. And on the graphic there, this is the vertical distance between the purple and red curves that represents the failure penalty. In later iterations, it is working to find better solutions. So it continues to breed these chromosomes or trial solutions and find better and better solutions. The only way you know that you have found the optimal one is to compare it with thousands of other intelligently selected trials. This often results in solutions, this is based on our findings, that we can reduce approximately 15 to 20% of the reinforcement, total reinforcement and labor costs and models that we optimize. One of the biggest advantages of this process is that the design is accomplished automatically as a byproduct. So rather than an engineer spending hours or even days producing a design, he or she can spend just a few minutes setting up optimization parameters and letting the optimizer do the rest. So I won't be demonstrating the entire PT design optimization workflow today in this presentation. However, if you're interested in learning more about preparing those models, I encourage you to review the PT design optimization help content, which you can access directly through RAM Concepts help menu. As Anne-Marie previously mentioned, these are also available as documents in the resources section. Both of these documents include best modeling practices that are very important for producing successful optimization runs.
Let me just say one thing about the tutorial. It's not just the step-by-step process. There's also a data set in there so that we get you set up with the model, and it's very easy to go through and like hone your skills working through the tutorial. So that you have them right now, just open RAM Concepts like that slideshow, go to the help pull down and find the tutorials. You can check them out right after our session today.
Thanks for mentioning that, Anne-Marie. In fact, if you do open that tutorial model, it includes the optimization results from a run that I've completed here. So you would see the convergence chart. And then also another advantage of that, you can just queue up an optimization to get a feel for how long it takes and things like that directly at the model. So no additional modeling input or effort is required on that front. So as I mentioned, I'm not really going to details of the workflow, but one part of the workflow that I want to cover in detail is how you can combine the recently added deflection check feature that was added in version 8.4 with the PT design optimization feature to completely automate the deflection control of PT concrete floors. So in other words, utilizing those two tools, RAM Concept can automatically add post-tensioning or change the tenon profiles to keep deflections below a specified deflection limit that you specify. So again, automatically without any manual iteration or effort on your part. So let's take a closer look at those steps and how you would accomplish that. So the first step is you need to define the deflection check limits, and that's shown on screen here. Those limits can be absolute deflection limits, so a total deflection, or they can be based on the span length. They can also be used for downward and or upward deflections. Each of those limits is associated with a specific loading or load combination, typically a service load combination. And we also offer a diff result layer. And if that's used, Concept will look at the deflection from the loading or load combination that is selected for the layer in the layer column and subtract the deflection for the loading or load combination that is selected for the diff layer. So that particular diff layer selection is especially useful for investigating incremental deflections after, say, partitions are installed, or reviewing instantaneous live load deflections. The next step is assigning those defined deflection check limits to design strips. This is done through the span segment properties by selecting specific user-defined deflection limits that are intended to be checked for that given span segment. You'll note that, or want to note that the actual deflection checks are completed at stations along the span segment. So they are not average deflections that are integrated across a cross-section like the design forces and moments are calculated in RAM Concept. If needed, though, you can also model a deflection check object. This was a new object that we added with those deflection check limits. And you can use those to review deflection hotspots that are not directly intersected by a span segment spine. So you may want to consider modeling one of those deflection check objects diagonally across the longest bay or largest bay so that it intersects the point of maximum deflection in the floor. Another use case for that type of object would be modeling one of those near a slab edge to enforce deflection limits for cladding. After the deflection limits are assigned, you're ready to start the optimization. And during that process, the failure cost penalties are associated with the deflection checks are processed exactly like they are for other design checks. So that failure penalty mechanism forces the optimizer to automatically weed out those possible solutions that don't satisfy the deflection requirements, and ensures that we're favoring the solutions that actually do control the deflections. After the optimization completes, you can load the optimal design in the model and review the deflection check results. The image on the left shows the deflection check status. In this case, all deflection checks have passed. They're shown in green. The image on the right plots the actual analyzed deflection that is displayed with the green curve against the deflection limit, which is displayed in blue. Showed on a previous slide that we don't recommend utilizing load history deflection layers with PT design optimization. And the reason for that is just the amount of time it would take to process those rigorous calculations. However, if you did have, or were analyzing a slab that was sensitive to long-term deflections, you still have the opportunity to load the trial in and then carry out those calculations and do a subsequent check after you load the optimal design. The tabulated results here are from an actual user model that was sent into us and we optimized in RAM Concept. That design was nearly complete, but it had localized areas where higher loading and longer spans were driving both stress failures and also deflection issues, and they were difficult to eliminate. And what I mean by that is we were adding post-tensioning in that area or changing the tendon profiles, and we found that while we could eliminate the failures in that localized area, we were just creating a different design issue or a different failure, different deflection concern in a nearby area of the floor. And that type of problem is pretty typical when using finite element analysis products like RAM Concept. You'll find that making a small tweak in one area just leads to a different result in a different area of the floor. So just focusing on the results in the table, you can see that the PT design optimization feature did a much better job at optimizing this particular design. Not only was it able to eliminate the service failures, but it also reduced the deflection by nearly half. And it also surprisingly accomplished that with less post-tensioning rebar and stud rails, which was surprising. To summarize then, the enhanced capabilities and value that can be unlocked by combining PT design optimization with RAM Concept. We eliminate the need for tedious manual iteration or value engineering, which often happens at the tail end of the project. And we do that by completely automating the design process, including automating deflection control. So rather than spending days trying to find an optimal design, we can invest just a few minutes to set up the model for optimization. And as I mentioned before, just let the optimizer do the work. And while the optimizer is working, you and also your desktop is free to focus on other engineering tasks. So that's an added value. Instead of focusing on those tedious manual iterations, you can add value to your project by focusing on detailing, documentation, coordination, or any other thing that you find that adds engineering value to the project. Before we close, there was one added capability that it did not cover that I think is worth mentioning. Emery alluded to this in the introduction, and that is the ability to rapidly compare different structural schemes using PT design optimization. So an example of that is you can use the optimizer to quickly complete parametric studies to see how different things like concrete thickness or concrete strengths affect the total cost of the floor. So what you're doing there is you're running different scenarios in parallel and then saving those results in a single RAM concept file for just easy review. The value added then is engineering time savings, which, as I mentioned, it can be amount to a week for a complicated floor. And then a secondary value, but also very important, is delivering cost-effective post-tension designs. Our studies have shown that you can expect between 15% reinforcement reductions for typical floors and maybe even higher for complex floors. And if you are designing with codes other than ACI 318, those typically aren't bounded by a minimum pre-compression limit, and those material gains are even higher for those codes.